So thank you for the introduction, Jan. So my talk today will provide an overview of the various Sutterpatch data structures and discuss how to access, export, and import data. First, a quick overview of Igor Pro, which as Jan mentioned is the foundation for our Sutterpatch software. Igor Pro is an interactive software package designed for the analysis and visualization of scientific and engineering data with the main goal of producing publication quality graphs and page layouts. Igor Pro has been used by tens of thousands of technical professionals since it was introduced in 1989. I have been using it since 1990 when it was first a Mac 2 application. Igor Pro provides a complete scientific toolset to quickly analyze and graph large data sets with built-in statistical, curve fitting, and image processing functions. Igor Pro is a powerful programming environment with a full-featured symbolic debugger. It's a perfect environment for creating and testing automatic data analysis procedures and building custom graphical interfaces. There's no better example of its capabilities than our own Sutterpatch software. I would like to reiterate how powerful Igor Pro is and that custom macros and procedures can be easily combined with Sutterpatch, as we do not block any of its features. If you have any specialized analysis needs, then there's no better toolkit, since there will be no need to export data or purchase any additional software licenses, as a 3-user license is included with all Sutter amplifier systems. As I was preparing this talk, I realized that an understanding of the Sutterpatch data structures and how data can be accessed was an essential part, especially when it comes to data export and presentation. So I would like to spend some time describing these various data sets. Our goal early on was to use as much of the native Igor Pro behavior as possible. The packed experiment file was a perfect fit. With the release of Igor Pro 9, HDF5 packed experiment files were also an option, but there were still limitations, especially for the high bandwidth data produced by our DPatch amplifier systems. Therefore, the option to store all the Sutterpatch data to a separate HDF5 file was added. Now, why use a separate HDF5 file? Well, two main reasons. One, only modified or newly added data are updated, which greatly improves performance, especially with large data sets. Typical PXP files from Igor are completely updated with every saving, which sometimes could take a very long time. Accessibility via third-party applications that support HDF5 files directly. For example, I know of a number of users who are already using our files with MATLAB and with Python. File settings can be configured in the Set Preferences, Files and Naming windows. An experiment file is always created, but with this option enabled, it would only contain Igor-specific objects. What do I mean by that? A custom layout, graphs, results from custom user macros or procedure files will all be stored in that experiment file. At the very top of our data sets are the individual signals. Signals are either acquired, created by a virtual math instruction, or imported. Each signal data is stored in a 2-dimensional 64-bit double precision or 32-bit single precision floating point wave. The wave has X number of rows, computed by sweep duration times sample interval, with N number of columns for each sweep. Default data precision is 64-bit, which can be changed in the Set Preferences, Files and Naming window. Virtual signals will always be 64-bit double precision. Also, Sutterpatch data is always stored in native units. Amps, volts, etc., always properly scaled. Unlike other data acquisition applications that require several gain and offset factors to be applied to have a valid data set. There are a variety of analysis results created in Sutterpatch. They could come from real-time measurements and graphs, which were executed during series acquisition or during post-hoc reanalysis, or generated by one of our analysis modules, either action potential, synaptic event, or single channel analysis. Analysis results can be easily accessed from the analysis editor window. Analysis results can be either shown as a table or graph, and they could have different wave formats. Tables are stored as 2-dimensional 64-bit double precision floating point waves, where rows are the sweeps and each column has a specific result. Dimension labels are used to properly mark the columns. Sutterpatch provides table formatting settings in the Set Preferences data export window for making these waves easier to read and export. As I mentioned earlier, we use native units for storing the data, but for display and export, the table data is parsed based on these settings. A powerful feature of Sutterpatch is the metadata stored along each dataset. Metadata comes from a variety of auto-generated system parameters, for example, amplifier or data acquisition settings, or from any number of user-selectable parameters. These parameters are all based on the selected metadata levels specified in the Set Preferences metadata window. The full detail option provides the ability to select from over 600 parameters. Now, you don't have to use all 600 parameters, but you have many options to choose from. Metadata is stored in a 3D text wave, where rows are the meta parameters, columns are signals, and layers are the various meta tags. Again, dimension labels are used to properly mark the meta parameters. The experiment structure reflects the structure of the experiment file, i.e. the sequence of paradigms and routines that were executed. This is a single two-dimensional text wave with dimension labels for each column. Speaking of routines and paradigms, routines and paradigm copies are stored as well, but those waves are encoded and cannot be read directly. More on that later. Finally, images, either acquired via our camera module or imported, are stored in a 3D wave using PNG encoding. Okay, now let's access these data waves. All the data waves that I just described exist within the Igor Pro environment, which can be viewed with the Igor's data browser. For most Sutterpatch users, they will rarely need to look at the individual waves, as Sutterpatch provides several editors to organize, view, and in some cases modify. If you're writing your own macros or procedures, the data browser can be very useful for getting a variety of wave information, as well as tools for viewing the data as a graph or a table. For most users, the Data Navigator window will be the main access point to visualize, analyze, export, and import data. The data is displayed as a tree structure with the name of the experiment file at the very top, followed by paradigms, either auto-triggered or planned, which may or may not include a routine level with signals and sweeps. The Enable Marks feature allows selecting or unselecting data for display, analysis, or export. A variety of options for marking, unmarking, including equations and value lists, are available from the right-click menu. These options will change based on the selected tree branch. The Data Navigator also has options to filter the data tree based on specific metadata parameters. Single or multiple metadata parameters can be selected. Enabling the tree filter will recreate the data tree with only the relevant entries. In this example, only series that included signals acquired in current clamp recording mode are shown. Please note that this filtering has no impact on the actual stored data. Now I would like to review some of the options for the various tree levels. First, the paradigm level. In addition to the exporting, marking, and unmarking options, a useful feature is Review Paradigm. This selection will display a time course overview of all the acquired series within this paradigm level with the appropriate timing information marks. The info section, shown here, will provide links to paradigm-specific information. For example, if a planned paradigm was used, then a copy of that paradigm would have been stored, which can be viewed by selecting this link. As I mentioned earlier, this copy is encoded, but it can be easily copied to your active paradigm pool where it can be used and/or modified. If images were stored, individual links to those pictures will be shown as well. As I mentioned earlier, metadata has many layers. A link to the paradigm-specific metadata would be available in the info panel as well. Favorites could be defined in the same way as with the Data Navigator filtering. Metadata parameters can be sorted either by event, parameter, or by favorites. This metadata filtering and sorting is available on all tree levels. Like the paradigm level, the routine level has its own options as well. Review routine will provide a time course overview of the acquired series. The info section is updated for routine-specific information. A link to the routine-specific metadata with the same review options as described earlier. A link to any real-time measurements and graphs stored in the analysis editor. And finally, a link to the routine copy for displaying routine settings and/or dynamic clamp settings if they were active. As with the paradigm copy, the encoded routine and dynamic clamp settings can be copied to their respective pools. A good use scenario here would be to replicate an experiment from a shared data file. Copying the pool entries would allow you to have the exact settings without having to manually enter them, which will allow you to replicate the experiment of that data set. Finally, the signal level. As you see, there's no info window, just an expanded preview. The unique options that I would like to point out is starting one of our analysis modules, averaging sweeps, and displaying and editing the signal data in native Igor graphs or tables. You may have noticed that there are two graphs shown. The one on the left includes only the marked sweeps, while the one on the right is all the sweeps that were acquired. Throughout all the various levels that we just saw, there was data export selections. Data export uses predefined settings that are set in set preferences data export window. Shown here are the various file types that can be used. Each file type may have specific options that will also need to be set. For ABF format, we use header version 1.85 requirements. The second option is for copying and converting data within Igor. No external files are created here, just waves in the specified target folder within the Igor environment. This option was added for customers who had custom analysis functions that required 1D waves, and we expanded on it to make it more usable. Throughout the various Sutterpatch windows, we have the copy to control. This control provides the simplest tool for exporting, either directly to the Sutterpatch notebook or to the clipboard for pasting into other applications. The Sutterpatch notebook has a special version of this control as well, which includes printing and saving the notebook contents. With version 3 of Sutterpatch, the notebook window can handle any combination of graphs and text. Sorry, what I didn't mention before, that all the windows that I show here and all the options are with Sutterpatch version 3. As I mentioned with the analysis results, the copy to control also uses the table formatting preferences. One quick note, if you're pasting into Excel, exponential notation data is required, otherwise it will not be properly read. Copying to an Igor layout page provides all sorts of publication quality options, as each item in the layout page is its own unique object and it can be handled any way that you would like. You could expand it, you could change the grids, you could change colors, anything that you would like, and then that page can then be printed or stored as a PDF. All graphs in Sutterpatch have native Igor options available via the right-click menu for modifying, exporting, and then saving or printing these graphs from the file menu. Now that covers most of the export options. Now let's talk about data import. As mentioned earlier, data import is handled from the Data Navigator. Importing data, whether it be a Sutterpatch experiment, a Sutterpatch HDF5 file, Patchmaster, or ABF file, would be added to the current experiment file. Experiment files can have any length and include as many data sets as needed. Importing various experiment files into a new file will allow you to organize all the data into a single file while leaving the original files intact. So if you have a paper that you're working on and you want to put specific data sets into a file to go along with it, this is a nice, easy way to do it. Within this new modified file, you could also do things like discard routines and or paradigms. ABF file import is limited to ABF 1.85 and above files, ABF 2.0 to 2.09, and why they're separated is because they have different header types. We only support gap-free and episodic stimulation modes. I believe ABF, it's mode 3 and 5. There are several limitations with channel signal assignments that Sutterpatch relies on, but is not directly available in ABF files. Every effort was made to predetermine these settings, but user confirmation is required for the import to continue, and that's done through this map channel connections window. One more thing that I would like to mention, we have seen many ABF files that were created by third-party applications that do not adhere to the ABF header requirements, which may lead to either a failed import or very strange settings. For Heka Patchmaster, we support their so-called 2x80 data files. Patchmaster Next uses a different file format that we are currently working on. Now, one last bit of general information that may be useful. EaglePro tutorial videos are available on their website, while ours are available on our YouTube channel. Well, with that, I'd like to thank you for your attention and I'd like to pass to Jake.